Have a great day, dear students. Now I am presenting you a video lecture on Discrete Time Fourier Transform, that is DTFT. As I have told you in the class, because of lack of time, we are presenting you DTFT in the form of video lecture. I request all the students to go through this and study DTFT. Of course, DTFT is very simple to learn, and few problems are also worked out in this video lecture. This is course material courtesy. The course material is taken from various websites and various books. There are a lot of material on signals and systems available. Okay, let me introduce Fourier. You already know Fourier. He is a man from 18th century. He has gifted two important tools for analyzing signals and systems. They are Fourier series and Fourier transform. His inventions and his contribution to mathematics and engineering is enormous. Okay, it has got a wide lot of applications. The Fourier series and Fourier transform both. This Fourier series and Fourier transform are used not only in signals and systems, it is used in many real-time applications like image processing, signal processing, speech processing, the FFTs. The first Fourier transforms are used in digital communication. Everywhere in real-time analysis, everywhere you have Fourier transform playing its role. So we have to have gratitude for Fourier for his great contribution to the scientists and also to the engineers. Now there are two types of tools from Fourier. One is Fourier series and another one is Fourier transform. Okay, so Fourier series you have already studied. Let us have a small review. So Fourier series gives us a method of decomposing any periodic function into a sinusoidal components. Okay, so if the signal is periodic, you will be able to write the signal as sum of weighted components of sines and cosines. Okay, so we can say that Fourier transform is series is an expansion of periodic signal in terms of an infinite sum of sines and cosines. So let it be any signal, let it be a square wave or triangular wave or anything of any shape, but it should be periodic. So if it is periodic, you will be able to write it in the Fourier series form. And basically you are supposed to have infinite number of terms, but sometimes it will be less number of terms with its similarity with the sinusoids. Okay, so this Fourier series makes use of the orthogonality relationship of sine and cosine functions. Okay, now this is about Fourier series. Now come to Fourier transform. This is also a mathematical tool which is magical, and this transform decompose any function, let it be periodic or aperiodic, into sum of sinusoidal basis functions. So this also uses sinusoids, that is e power j omega or e power j theta, that particular function, and this decomposes any periodic or aperiodic signal with a basic function which is sinusoidal again. Okay, so take any transform, the function, the given function will be multiplied by another function called as the kernel function, and the resulting product will be integrated over a suitable limit. So take it as a Laplace or Z transform or Laplace transform or any transform. You will have the function multiplied by a kernel function and integrated over a limit. Okay, so this what is the necessity for a transform is the transform converts as function from one domain to another with no loss of information. There will be no loss of information, and the signal will be converted from one domain to the other domain. Fourier transform basically converts it from time domain to frequency domain, or from the spatial domain to the frequency domain. Okay, so this is an example. In the time domain, if you see a sine wave, it could look like this. Okay, so this is a sine wave. It has an amplitude of 100 and it has a frequency. The frequency is from 0 to Yeah, here 0 to 5. Okay, so it has a frequency and it has an amplitude. So this is how you view the signal in the time domain. Now if we take the transform of this, okay, how it looks is at this particular frequency, there is a sinusoidal wave whose amplitude is 100. So this tells how the properties or how the amplitude change over the frequency. So the x-axis you have frequency, and in the y-axis you will have amplitude. Okay, amplitude or phase. Okay, so this is how the time domain signal is viewed in a frequency domain. Okay, so this is the basic purpose of any transform. It converts a signal from one domain to the other domain for viewing the property, viewing it differently, in a different way. You look at it at a different point of view. Okay, so that is the purpose. Okay, so now let me list the different Fourier tools we have already seen in the class as well as here. Okay, so there are basically there are two tools, Fourier series and Fourier transform, and it can be split into four depending on the type of signal for which it is being used. Okay, so now continuous time Fourier series is used for continuous time periodic signal. Okay, and then you have discrete time Fourier series also, which will be used for discrete time periodic signal. Okay, and then you have continuous time Fourier transform, which is used for continuous time aperiodic signal. Basically it is used for aperiodic signal because Fourier series cannot be used for aperiodic signal. So this Fourier transform can be used for aperiodic signal and continuous time, and even if the signal is periodic you will be able to see the Fourier transform. Okay, the example is this example. This is a periodic signal. Okay, this is a periodic signal, and when you do the Fourier transform you will get the Fourier transform as a spike, at the particular frequency where it is with which it is existing. So Fourier transform can be used for periodic as well as aperiodic signal, for any signal. And then if the signal is discrete in nature, discrete in time domain, then you call it as discrete time Fourier transform. Okay, so it is only Fourier transform and Fourier series. When it is applied for continuous time signal, you call it as continuous time Fourier series, continuous time Fourier transform. When you apply it, use it for a discrete time signal, you call it as discrete time Fourier series and discrete time Fourier transform. That's it. Okay, okay. So these are the different tools you have studied. Okay, you have to go through all these topics because Fourier is there in your syllabus. Okay, now one slide for continuous time Fourier transform. So in continuous time Fourier transform called as CTFT. Okay, CTFT, if x of t is the input, when you take the Fourier transform you get x of omega. Okay, capital X of omega, and capital X of omega is given as integral minus infinity to plus infinity x of t e power minus j omega t dt. So this function is called as the canal function in this case. Okay, e power minus j omega t dt. And if you want to have the inverse, then you will, if you take the inverse of x of omega, you will get x of t, and it is given by 1 by 2 pi integral minus infinity to plus infinity x of omega e power plus j omega t d omega. Okay, so these are the two equations. The first equation is called as synthesis equation. Analysis equation. The second equation is called as synthesis equation. Okay, so this diagram, if you give a square pulse, you will be getting a Zin pulse in the frequency domain. Okay, so this is the time domain signal. This is the transform signal. It looks like this. Okay, now let us see what is discrete time Fourier transform, DTFT. So discrete time Fourier transform is for discrete time signals. Okay, so discrete time signals are represented as x of n. So if you have x of n as the input, your output will be called as x of omega. For a discrete time signal, you have to use this omega. This is a capital omega. Okay, capital omega, and x of omega will be given by the formula summation n is equal to minus infinity to plus infinity x of n e power minus j omega n. The same kernel function, okay, but instead of integral you will have summation because x of n is discrete. So summation n is equal to minus infinity to plus infinity x of n e power minus j omega n. This equation is called as analysis equation. Now if you want to synthesis your signal back, okay, that is your x of n. If you want to synthesis get it back, you will get x of n by this formula. So 1 by 2 pi integral over one period of time, okay, and capital X of omega into e power j omega n d omega. So why it is summation here and why it is integral here is, here your input x of n is discrete, and when you find out x of omega, this x of omega is going to be a continuous spectrum only. Your spectrum will be a continuous function. It is not discrete function. Even though the input x of n is a discrete function, x of omega will be a continuous function. So you have to you have to integrate it, and why it is over 2 pi is, there is a property of a discrete time Fourier transform that the x of omega function will be periodic with period 2 pi. Okay, so for every 2 pi, your function x of omega is going to repeat only. So if you take the integral over one period, that is 1 over 1 0 to 2 pi, or from minus pi to plus pi, it is enough. So this is the formula. Okay, now x of omega can also be written, will be in this form. It will be complex. So you will have a real part and an imaginary part. So in the rectangular form, you can write it like this: real part of x of omega plus imaginary part of j into imaginary part of x of omega. And then in the polar form, you can write it as mod of x of omega, that is magnitude, into e power j into angle of x of omega. Okay, so this is all about the DTFT function. Okay, now we'll see some properties of Fourier transform quickly. The same properties, what exists there. What is different is the first one. First one is different. It is not there for a CTFT, that is continuous time Fourier transform. Okay, so x of omega is periodic with a period 2p. Okay, so this property is not there for CTFT. Okay, so x of omega, it repeats for every 2 pi. So 2 pi into 1, 2 pi into 2, 2 pi into 3, etc. So this is the periodic property of x of omega. And then symmetry property is given by, if x of n is real, x of minus omega will be equal to x conjugate of omega. Okay, and when you take the real part as the magnitude function, it will be even. If you take the imaginary part as the angle phase function, it will be odd. Okay. Now illustration of symmetry of x of omega. So I told you the magnitude function will be symmetric. So for example, they have taken x of n is equal to a power n into u of n. So for a power n into u of n, a less than 1, for a less than 1, the signal a power n into u of n will be a decaying exponential signal. You must be knowing that it will be a discrete time signal, but it will be a decaying exponential signal. So x of omega is equal to 1 by 1 minus a into e power minus j omega. We are doing the same example later. Okay, so if I take the mod function of this, I am getting like this. Okay, so if you take it from 0 to 2 pi, you can take the magnitude function from 0 to 2 pi, or from minus pi to plus pi. Both are equivalent. Okay, so if you take from 0 to 2 pi, after 2 pi it is going to repeat. Okay, if you take from minus pi to plus pi also, it is going to repeat. Okay, so usually the function will be defined from minus pi to plus pi. Okay, either from minus pi to plus pi or from 0 to 2 pi. Okay, so the magnitude function is always symmetric and it is periodic. And similarly, the angle function for this particular function, okay, if you find the angle for different values of pi, different values of omega, okay, for 0 up to minus pi and plus pi, you are going to get this function. So this is antisymmetric, or it is an odd function. Uh, Now let us see the properties of DTFT. It is similar to the properties of continuous time Fourier transform. So if the time domain signal is shifted by n naught, x of n is shifted by n naught, then if you take the Fourier transform, the original transform will be multiplied by e power minus j omega n naught. Okay, e power minus j omega n naught. And then frequency shifting, that is if you multiply your signal by e power minus j omega naught n. Okay, this is a cosine, this is a sinusoids. Okay, here you have sinusoids. So when you multiply that, it is called as frequency shifting, and it will be the x of omega will be shifted by omega minus omega naught. Okay, linearity is a into x1 of n plus b into x2 of n. Fourier transform will be a into capital X1 of omega plus b into x2 of omega. Okay, this satisfies both the property, that is multiplication, scaling, the scaling factor a and b, and addition. So if scaling and additive property both are satisfied, then it is said to be linear. Okay, and now next is Parseval's relation. Already the same relation exists in CTFT also. So Parseval's theorem gives you the energy spectrum. So summation n is equal to minus infinity to plus infinity. X of n the whole square is nothing but the energy of a signal. Okay, the energy of the signal can also be obtained by 1 by 2 pi integral over one period x of omega the whole square d omega. Okay, and then the important property, convolution property. If you do convolution in the time domain, in the frequency domain, it is equivalent to multiplication. Okay, so h of n convolution x of n. If you take the Fourier transform, you will get h of omega into x of omega. And this one you already know. If h of n is the impulse response, x of n is the input, h of n convolution x of n will give you the output. Okay, and this one is x of omega is the transform of this, and this convolution operation becomes multiplication here. And if the input is e power j omega naught n, you will get the frequency response. Okay, so these are all there in the introduction. Now we'll go to some problems which is worked out. Okay, Fourier transform examples. Very few examples, all simple examples only. This PDF will also be uploaded in the Moodle. Okay, in Moodle, so you can refer to that. So now first take the signal del of n. So find the Fourier transform of del of n. So x of n is equal to del of n. X of omega will be equal to summation n is equal to minus infinity to plus infinity. X of n e power j omega n. That is the formula. Okay. So now x of n is nothing but del of n. So you are putting del of n over here. E power minus j omega n. Now del of n, you know that it exists only at n is equal to 0. Okay. So at the origin, only at n is equal to 0 it exists, and its value is 1. So the value is 1, and this will be valid for only for n is equal to 0. So all the other places it is 0. So you have del of 0 into e power minus 0. Okay, so e power 0 is 1 and del of 0 is 1. So the output, so the transform is 1. So for a del of n signal or for impulse signal, the transform, Fourier transform is equal to 1. Okay, now come to the next second sum, u of n. So if input is equal to u of n, that is unit step function. So again I am writing the formula. x of n into e power minus j omega n. Now you know that u of n, its value is 1 and it exists from 0 to infinity. So the range changes from 0 to infinity and u of n is 1, always 1. So you just have e power minus j omega n. Okay, so putting n is equal to 0, 1, 2, 3, etc. We have 1 plus e power minus j omega plus e power minus j 2 omega plus e power minus j 3 omega plus something plus up to infinity. Okay, so now you have a summation formula 1 plus a square plus a cube plus etc. up to infinity will be equal to 1 by 1 minus a if a is less than 1. Okay, so this value is going to be less than 1. All these values are going to be less than 1. So you can use the formula and you get the transform as 1 divided by 1 minus a. So a is here e power j omega. Okay, so 1 divided by 1 minus e power j omega. So this is the Fourier transform of u of n, that is unit step function. Okay, now come to the next one. That's the signal is del of n minus k. Okay, this is also a impulse, but it is shifted. So del of n minus k. So summation n is equal to minus infinity plus infinity del of n minus k into e power minus j omega n. You know that del of n minus k is equal to 1 only for n is equal to k, and it is equal to 0 for the other things. Okay, so now you will have if n is equal to k. So put n is equal to k, you will get del of 0 which is equal to 1, and put n is equal to k, here you will be having e power minus j omega k. So 1 into e power minus j omega k, so e power minus j omega k is the answer. Okay, hope you all are following. Okay, now you find out the transform for u of n minus k. So u of n minus k, we can use time shifting property. Okay, because you already know the transform for u of n. So the transform for u of n is 1 divided by 1 minus e power minus j omega. Now this is shifted by k. Okay, so if there is a shift, it has to be multiplied by e power minus j omega k. K is the shift value. So by time shifting property, Fourier transform of u of n minus k will be equal to e power j omega k, because k is the shifting value, divided by 1 minus e power minus j omega. Okay, so simple. So whenever u of n transform is this, u of n minus k transform is this into this factor e power minus j omega k as per the time shifting property. Okay, so you need not summate it again. If you summate it, you will summate it from n is equal to k to infinity, and then you have to find out it properly and so on. Okay, so this is the simplest method. Using the time shifting property is the simplest method. Okay, now come to the next sum. X of n is equal to a power into u of n. The diagram of this, what is it? The magnitude and phase function of this only is shown in the PPT. Okay. Now let us see a power n into u of n. So again, a power n into u of n is a exponential signal depending on the value of a. So if a is less than 1, it will be a decaying exponential signal. If a is greater than 1, like 2 etc., 2 power 1, 2 power 2, 2 power 3, it will be a growing exponential signal. If a is less than 1, like 0.9 or 0.5, it will be a decaying exponential signal. Now here it must be a decaying exponential signal, because we have a condition that Fourier transform for a signal exists only if the signal is absolutely summable. Okay, maybe I forgot to tell that, or we have already done that for CTFT. That is, the Fourier transform for a signal exists only if the signal is absolutely summable. Okay, so exponential signal will be summable only if it is decaying. So a must be less than 1. Okay, so here I haven't given a is less than 1, but it is less than 1 if Fourier transform has to exist. Okay, now we are just writing this function as u of n is there. Okay, u of n is there. The limit changes from 0 to infinity. From minus infinity, it changes to 0. So summation 0 to infinity a power n e power minus j omega n. U often value is 1, so it is not written here. Okay. And then summation n is equal to 0 to infinity a into e power minus j omega the whole power n. Now this is your base value. So okay, now if you expand, it will be 1 plus a into e power minus j omega plus a square into e power minus j to omega, etc. up to infinity. So when you summate this, these values are less than 1, you can use the same summation formula which is given by 1 divided by 1 minus a. So a is this here, so it is 1 divided by 1 minus a into e power minus j omega. Okay, done. Now next sum. You have two impulses shifted right and left. So del of n plus 2 is a left shifted signal. This is a right shifted signal. So if you write the transform for this, it is e power j to omega by time shifting property. Okay, for del of n it is 1, and del of n plus 2 it is e power j to omega into 1. For del of n minus 2 it is e power minus j to omega into into 1. So when you have these two here, it is e power j theta minus e power minus j theta. If you have by 2j, it will be sine to omega. Okay, so now I am multiplying and dividing by 2j, so we get 2j into sine to omega. Okay, so this is the answer. Okay, now the seventh sum, let us have a finite duration sequence. So these are some set of values, finite duration 1, minus 1, 2, 3. Okay, here there is no arrow mark given. That means the first sample is x of 0. It is the sample for n is equal to 0. So for x of 0, the value is 1, x of 1, the value is minus 1, and so on. Okay, so you have 4 samples for n is equal to 0 to 3. So the summation will now, the range will be from n is equal to 0 to 3 because it is a finite duration sequence, x of n e power minus j omega n. So now it is simple, x of 0 is 1 and x of n is equal to 0, so e power 0, and then x of 1 is minus 1, so minus 1 into, put 1 here, e power minus j omega, plus 2 into e power minus j 2 omega, substituting n here, okay, plus 3 into e power minus j 3 omega. Okay, here nothing can be combined to make a cos or sine term, so just leave it as it is. Okay, that's it. Okay, now the next sum, x of n is equal to 0 for n less than 0. It is equal to a power n for a limited value for 0 to q, and it is 0 for n greater than q. So this a of n exists for a limited value of q. Okay, so a is a non-zero real constant and q is a positive integer. So the range will become n is equal to 0 to q because it exists only from n is equal to 0 to q, a power n into e power minus j omega n. So taking n common, it will be a into e power j omega the whole power n. Okay, now you have to use the summation formula for a limited number of terms. So from n is equal to summation n is equal to q1 to q2. The range is known, not infinity. R power n will be given by r power q1 minus r power q2 plus 1 divided by 1 minus r. Okay, so this formula also you note it down for limited number of terms in the summation series. Okay, okay, now as per this, it is given by r is equal to a into e power j omega. So first n is equal to 0, so r power 0 it is 1 minus r is this a into e power minus j omega the whole power q plus 1. Already there also it is q, so it is q plus 1 divided by 1 minus r. It is very, very simple. All are very, very simple. Okay, this periodicity I have already told, these points I have already told in the PPT. Okay, properties also we have already discussed, so no need to go through it again. Time shifting, frequency shifting. Okay, time reversal. Uh, um, Time reversal is if I have x of minus n, Fourier transform of x of minus n will be capital X of minus omega. Okay, okay, and then a differentiation in time domain. So if the signal is differentiated in the differentiation in the frequency domain. Okay, so if signal is multiplied by the time variable n, the time variable is n here, as it is discrete time signal, the time variable is n. So Fourier transform of n into x of n can be obtained by j into d by d omega of x of omega. Okay, you have to differentiate the Fourier transform in the frequency domain. That's why it is called as differentiation in frequency domain. So Fourier transform of n into x of n will be equal to j into d by d omega of x of omega. Okay, and then convolution theorem already we have seen. If you have the signals convoluted in the time domain, it will be equal to the multiplication of their transforms. Okay, in the frequency domain, and then convolution in the frequency domain. So if you multiply two signals in the time domain, in the frequency domain their transforms are convoluted. Okay, this is convolution. And then Parseval's theorem I have already told you. Okay, Parseval's theorem I have told you. And then inverse Fourier transform. This is the formula x of omega. If you do the inverse Fourier transform, I will get x of n, and x of n is given by 1 by 2 pi integral minus pi to plus pi. Okay, because you need to integrate it over one period of the function. The period of the function is 2 pi, as already seen as the periodicity property of the Fourier transform. So you can integrate it from 0 to 2 pi or from minus pi to pi. Okay, it is easy to do from minus pi to plus pi. Okay, and x of omega e power minus j omega and d omega. You can do it on both the way. So if any inverse Fourier transform is asked, use this formula. And okay, hope this video is useful and you all understood this. If you have any doubts in any problems or anything, you can approach any one of us, or you can approach me in the 6th floor in my cabin. Okay, thank you. Good day. Bye.